Okay, so I think I'll actually start the colloquium. Professor Acharya, can you hear me?
Yes, I can hear.
Thank you, Professor Acharya, for joining.
Yeah.
Okay, so actually it's a pleasure to be back with the colloquium series after a little bit of a break. We have, of course, in this series, we host all sorts of chemists, all sorts of scientists under the umbrella of natural sciences faculty. And just for Professor Biju, who is our visitor today, the colloquium series is as old as TIFR itself. It was started by our founding director, Professor Homi Bhabha. And the idea was that when Bhabha would come to the institute, at least on Wednesdays, because he will be busy with other atomic energy related activities across Bombay, including visiting BARC. He would make sure that he would meet with all the faculty members for lunch, and that's where the concept of the faculty lunch comes from. And also, he would like to see one of a visitor come to TIFR, and there could be a colloquium. And we are maintaining this tradition, and thank you for joining us from Bangalore. And I also wanted to mention that the series has actually evolved such that it has allowed for people within the institute to crosstalk not just with the speaker, but also within themselves, because the colloquium is considered to be a general series for everyone to attend and listen to what is happening in different areas of science. So before I move on formally for the actual talk, I would like to briefly introduce Professor Biju. So Professor Biju actually is an organic chemist, and we don't often host organic chemists in the institute, but in the colloquium series. But this is sort of a important occasion because there are many sorts of myths about organic chemistry. In fact, physicist at the end, Ankit, is sitting here. So thank you, Ankit, for coming. But all those who actually have myths about organic chemistry, this is a talk where you can sort of sit down and sort of join in and see how an organic chemist thinks. Okay, and it's very rational, and there's nothing very sort of magical about it. So it's also sort of a deconstruction for everybody. So Professor Biju actually is a professor at the Department of Organic Chemistry at the Indian Institute of Science, Bangalore. He is leading organic chemistry from the country with a huge amount of contributions in different areas of organic chemistry with respect to natural sort of design of complex organic molecules and frameworks. Biju actually received his MSc from Sacred Heart College in Kerala, and this is in Thevara, Cochin, near Cochin. Okay, and then his PhD, he did his PhD in NIISc, which is the CSIR Institute with Dr. Vijay Nair in Trivandrum, and this is where I think a place where Biju also saw lots of photochemists grow with him. So, and supramolecular chemists and photochemists. Subsequently, Biju did his postdoctoral sort of tenure in two places. First at the National Taiwan University in Taipei with Professor Tian Yu Lu, if I did the pronunciation correctly. And then he was Humboldt Fellow in Germany with Professor Frank Glorious. And this was in Münster, Germany. After his two of these postdocs, Biju came back to the country, and we are happy that he came back and is part of our country's treasure, where he actually sort of started his independent research career first in NCL Pune, which is sort of the hub of many chemical research in the country. It used to be very, very rich with different kinds of chemical technologies being generated in the country. After 7 or 6 years in NCL, he moved to IISc Bangalore, where he is in the Department of Organic Chemistry. And he has been there ever since. His research focuses on the development of transition metal-free carbon-carbon bonds, as well as carbon heteroatom bond-forming reactions. And more sort of appropriately, he actually uses this with arine chemistry, different kind of arine chemistry, and what he's going to talk about, N-Heterocyclic carbenes, he uses as a framework to develop these systems as a reactive framework. Because of his work, wonderful work, for over the years, Biju actually has won many awards. I'm not naming the awards here, but he absolutely is one of the most important organic chemists. So you can imagine the awards he must have gotten. I'm not mentioning them. But he has been, because of his work, he has been the editor of the Journal of Heterocyclic Chemistry. He's been on the advisory board of synthetic letters, SynLet. He's been on the advisory board of Organic Chemistry Frontiers. That's right. And also in the Asian Journal of Organic Chemistry. All this editorial position is great, but one of the best things about Biju is if you are a student or a faculty member, you can always talk to him and ask a question, and he is very humble in his approach to answering those. So this is one of the best qualities that he has. So Biju, I welcome you for this colloquium. I'm sorry for a long introduction, and you can take over.
Yeah. Maybe you can come closer.
Yes, I think you guys should come closer.
Yeah. Okay, so thank you very much, JD, for the very kind introduction, and also the invitation to be part of this Wednesday colloquium, the traditional and very much important. So I was not knowing the real tradition, but very amazing that I became the part of this long tradition of Wednesday colloquium. Thank you very much for choosing me for this colloquium. So today, in the next 45 to 50 minutes, I will try to give you a take-home message on one phase of our research on carbenes, specifically N-heterocyclic carbenes. So we know that catalysis is one of the sustainable methods for forging carbon-carbon bonds or carbon heteroatom bonds. So yeah, I'm a synthetic organic chemist by training. I know that all of you are in different disciplines, and in the end, we all come under the umbrella of chemistry. So I hope at the end of the day, I will be able to give you some take-home message on catalysis using carbenes. So as I said, carbenes are the topic for today, the catalysis using carbenes. So before going into the details, just a brief introduction about catalysis in general. As I told, catalysis is one of the sustainable methods for forming carbon-carbon and carbon heteroatom bonds. And in the process, using catalytic techniques, one can make a lot of carbon-carbon and carbon heteroatom bonds, which leads to the formation of carbocycles and heterocycles of pharmaceutical importance as well as agrochemical importance. And among the various techniques for forging carbon-carbon bonds using catalysis, we know that there are three important techniques. One is the traditional enzyme catalysis, where the giant biomolecules act as catalysts for a given transformation. The second one is the transition metal-based catalysis, where one can use the metal catalyst for carbon-carbon bond forming reactions. As you know, this area has been recognized by Nobel Prize in 2010. And the third and an emerging area of catalysis is the one where one can use metal-free catalyst or simple organic molecules for forging carbon-carbon bonds. So this technique, the catalytic technique specifically, where one can use small organic molecules for a given transformation to catalyze, which is now known as organocatalysis. The name was coined by Professor David Macmillan in 2010. And again, you probably, all of you remember in 2021, this area of organocatalysis has been celebrated by Nobel Prize. So the Nobel Prize in this area of organocatalysis. So among the various techniques in organocatalysis or the vast realm of organocatalysis, there is a subclass where one can use carbenes as catalysts. And the catalysis using carbenes are really unconventional. And I hope by the end of my presentation, I will be able to convince you why and how carbene catalysis is unconventional. So to start with, we all know that carbenes are highly reactive intermediates in organic synthesis. So if you take a carbon atom, and we know that all carbon atoms are, or in a molecule, it is tetravalent. And when a carbon forms only 2 bonds and 2 electrons are not completely shared to have the octet in general carbon organic molecules, the carbon species, which is divalent or sextet, this type of species are highly reactive and short-lived because these species will try to get 2 more electrons to complete the octet. So such carbon atom or carbenes are the species with a divalent species with a carbon having 6 electrons in the outermost shell. Such species are called carbenes. And when we think about carbenes, we already know it is a diradical having 6 electrons in the outermost shell of this carbene carbon. Or in other words, carbenes are generally electrophilic or electron loving, or in other words, carbene needs 2 more electrons to complete the octet. So typical carbenes are dichlorocarbene. We know that dichlorocarbene is a key intermediate in rhymatimony reaction or the typical carbenamine reaction, where you can generate dichlorocarbene from chloroform in the presence of a base. A dichlorocarbene, or one can think about dicarboethoxycarbene. These carbenes are electron deficient or electrophilic in nature. So typically, these type of carbenes in general are electrophilic or electron loving, so that it can get 2 more electrons to complete the octet. On the other hand, there are a class of carbenes which, instead of the inherent electrophilic character, these species are nucleophilic in nature, where the carbene carbon is flanked by heteroatoms such as oxygen, sulfur, or nitrogen, where the mesomeric effect of the heteroatom or the resonance effect of the heteroatom pushes the electron density from the heteroatom towards the carbene carbon, thus making this carbene carbon more nucleophilic instead of the inherent electrophilic nature. So such carbenes are known as nucleophilic carbenes, or typically these type of carbenes are either dimethoxycarbenes or related carbene carbon attached to heteroatoms, where the mesomeric effect of the heteroatom is the key for the nucleophilic reactivity. When this type of carbene carbon, where a carbene carbon is flanked by heteroatoms, forms the part of a ring, where we have a carbene carbon flanked by nitrogen or sulfur, where the mesomeric effect of this heteroatom makes the carbene carbon nucleophilic instead of the inherent electrophilic character. Such carbenes are known as N-Heterocyclic carbenes or nucleophilic heterocyclic carbenes, which generally people abbreviate as NHCs. And these type of NHCs or N-Heterocyclic carbenes one can think about the imidazole derived, thiazole derived, or even the triazole derived species. One can generate in solution from the corresponding azolium salt. For instance, the imidazolium salt, thiazolium salt, or the triazolium salt. When we treat one of these species with a mild base, the CH proton alpha to this heteroatom is relatively acidic because it is alpha to a nitronium species. So one can abstract this CH proton using a mild base, which leads to the generation of these carbenes in solution. So this is how NHCs can be generated in solution from the corresponding azolium, generally, such as imidazolium, thiazolium, or the triazolium salts upon treatment with a mild base. Yes.
What is the advantage of using the technique carbon? Why can't I use carbene with the food and I use
So the typical diaminocarbenes. So the diaminocarbenes are also known in the literature. The cyclic nature gives a little bit rigidity to the carbon because otherwise it is more like flexible nature. So, but diaminocarbenes are known in the literature, the acyclic ones.
But is there any impact on their nucleophilicity if I have a cyclic?
It is not much, there is no impact on the nucleophilic nature per se, but the rigidity versus flexibility. So diaminocarbenes as such is also known in organocatalysis, but the N-Heterocyclic carbenes with the cyclic nature, it is relatively easy to tune the properties of the carbene, and one can install chiral element if we want to use this catalyst for asymmetric transformation, which is what I will be showing in the next slides.
Okay.
So it is relatively easy to install the chiral entity and preparation and the rigid nature of this carbene, which allows better reactivity.
Can I ask a question quickly
JD.
for everyone's clarification? So when I lose the proton there,
yes.
So what happens to the electrons there? In the sense, I still had a proton that I lost. So I still should retain the electrons. So how does the electron count work out?
So the base will abstract this CH proton, and this anion, this CN bond will be polarized towards the nitrogen, thus making it a neutral species.
Okay.
So this carbene,
so the two electrons go over there.
Yeah. So you can easily consider if you denote it by plus or minus, that makes a better clarification. Sure. So a carbene can also be represented instead of the 2 dot, a plus or minus, right? So yeah. So this is how yes. So this is either an imidazolium or thiazolium or triazolium. Okay. So when this imidazolium species, the nitronium cation is generated, this CH proton will be acidic. Okay. So once the base abstract this proton, now this CN bond can be polarized and neutralize this nitrogen, generating this species.
Like one should expect the pK of that NH proton should be.
There is no NH, right? Only CH. Only CH.
At the end,
yeah, so this N plus improves the acidity of the CH proton. Okay. Come, friend.
Yeah. Yeah, Rohit.
Please.
Okay. Yes.
Okay. Yeah, good. Yeah.
when we say that it became nucleophilic carbene.
So the oxygen is pushing electron towards that central carbon.
The nitrogen.
On top, the nucleophilic carbene. Do you expect that C single bond O bond length will be reduced on the first, in the top one?
The C double bond C.
The nucleophilic carbenes thing. Dimethoxy.
Dimethoxy. Yeah.
When it becomes like nucleophilic carbene, so now the electrons in the oxygen is pulled towards the carbon.
Yes.
Now, do you expect the bond length between the carbon and oxygen to get reduced when compared to single bond?
So the carbon and oxygen, say suppose you take this carbon nitrogen double bond. So
Yes.
this is always in resonance, right? So one can think of this nitronium here also.
Yes.
So once the carbene is generated, this CN double bond is converted to a CN single bond. So
Yeah.
naturally the bond lengths will increase, right?
When we come, if we compare the two typical CN single bond, do you think it will be shorter?
It will be slightly increased once the carbene is generated. But again, this is like it's like a imidazolium species. So it is aromatic species, right?
Yeah.
So if you consider a simple imidazolium species, this is aromatic in nature. And once this carbene is generated, this imidazolium species will be less nucleophilic, because to generate the carbene, one has to break the aromaticity. On the other hand, there are carbenes known without this carbon-carbon double bond. It's a carbon-carbon single bond, which is called imidazolinium,
Yes.
the saturated species. And that will be naturally more nucleophilic because there is no aromatic stabilization. Okay. So among these carbenes, now I will tell you a little bit about the important application of this carbene. So in the beginning, I told you carbenes are known for unconventional reactivity mode. So if you think about the addition of a carbene, a general carbene, so we have a carbene-carbon with heteroatoms flanked, which increases the nucleophilicity. So if this N-heterocyclic carbene adds to an aldehyde, and we know simple benzaldehyde or any sort of aldehyde, where the aldehyde carbonyl carbon is inherently electrophilic in nature. Okay, so the carbene can add to this aldehyde, thus converting the planar aldehyde to a three-dimensional tetrahedral intermediate. And now this tetrahedral intermediate can undergo a proton transfer to generate an enaminol, again a planar species. And by doing so, the addition of carbene to an aldehyde, what we basically did was just reverse the polarity of an aldehyde from inherent electrophilic nature to a nucleophilic nature, or instead, we can also say an acyl anion equivalent. Or in other words, if you see this enaminol, which is otherwise known as the Brislow intermediate, because the first proposal on this enaminol came from Ronald Brislow from Columbia University. And we can see that this enaminol is just like a hidden enamine, which can make this carbonyl carbon more nucleophilic instead of the inherent electrophilicity of the aldehyde. Or in other words, in summary, what we did was we reversed the polarity of an aldehyde from inherent electrophilic nature to a nucleophilic character by adding an NHC. And this property of reversal of normal mode of reactivity is known as umpolum, or the polarity reversal. And once this polarity reversal happens, by changing the electrophilic nature of an aldehyde to an acyl anion equivalent, this acyl anion equivalent can add to a second molecule of aldehyde in a benzoin type reaction where a new carbon-carbon bond is formed. Or in other words, it can add to an electron deficient carbon-carbon double bond to form 1,4-diketones. Again, a new carbon-carbon bond is generated. So this is the foremost application of carbenes in organocatalysis. And this is something unconventional to the typical reactivity of other catalysts in organic chemistry. So the take-home message is carbenes are useful for the polarity reversal of any electrophile. And what I showed here is the aldehyde electrophilic nature can be converted to acyl anion equivalent using carbene as organocatalyst. And the inspiration, yeah, Vivek.
Generate the acyl anion and then add.
Yeah, so this nucleophilic Brislow intermediate, it is what I want to say is, if you consider this part, it is just an enamine, right? So if you push the electron dense lone pair of electron from this nitrogen, this carbonyl carbon will be more nucleophilic in nature. And once this addition happens, then this O minus can push the electron and the carbene can be eliminated. I will show another slide, then it will be clear.
And can this be a catalytic like?
Yeah, this is catalytic. This is catalytic, basically catalytic. So the idea is the polarity reversal happens by the addition of carbene, and the catalytic cycle and all these things I will show in the subsequent slides. So all these reactions, all the carbene catalyzed reactions was the demonstration of the carbene type reactivity for all these reactions were first proposed by Ronald Breslau, and it is known even before 1958 that coenzyme thiamine has some remarkable role in many of the biochemical transformations, such as the non-oxidative decarboxylation of alpha keto acids, such as, say, if you take a pyruvic acid, it can decarboxylate in the presence of coenzyme thiamine to form acetaldehyde. And this acetaldehyde again can react to form acyloin. So all these transformations were known using simple coenzyme thiamine, but people did not know the real mode of action in most of these catalytic reactions. Initially, the proposal was the pyrimidine ring having this NH2 has some role. Then people thought that the thiazole ring has some role, but it was originally Ronald Breslau. He gave an interpretation that this carbene, which was represented in an ylide form, has this potential for generating the Umpolung species from an aldehyde via the generation of nucleophilic Breslau intermediate. And these intermediates, the Breslau type intermediates, as I said, the enamine, these were all a curiosity in 1958, just a proposal by Breslau, but it took several years, more than 50 years, to confirm the structure of Breslau intermediates by Professor Berkesel from Cologne. So most of the Breslau type intermediates from simple aldehyde and alpha beta unsaturated aldehydes, they are all fully characterized, and even the single crystal X-ray structure for these molecules are now available. So a similar demonstration by Breslau in 1958 was realized by single crystal X-ray analysis by Berkesel and Kovakers in 2013. So again, as I said, the foremost application of carbenes in organocatalysis is the polarity reversal. Say, if you look at the aldehyde symbol reactivity, aldehydes, as I said, it is electrophilic in nature. So typically, a nucleophile can add to the aldehyde, changing this planar molecule to a tetrahedral intermediate. And that is the typical reactivity of aldehydes, like an aldol reaction, Canova-Nagel condensation, all sort of aldehyde reaction where aldehyde carbonyl is electrophilic and a nucleophile can add, generating this tetrahedral intermediate. That is the typical reactivity. And if we consider the typical reactivity of aldehyde with the, and I'm sure some of you will recollect this person. So Ben List from Max Planck Institute, who won the Nobel Prize in Chemistry in 2021 for his seminal contributions in organocatalysis. And if we see the polarity reversal using carbene catalysis, where the carbene adds to the aldehyde, generating the Breslau intermediate or the acyl anion intermediate, we can just say that this is just a reversal or ulta. So in all the carbene catalyzed reactions, starting from aldehyde, one can think or one can compare with the smiling face of Ben with a inverted structure of Ben, where carbene can do an unconventional reaction. How? The carbene can add to the aldehyde, generating the tetrahedral intermediate, and then a proton transfer, thereby doing the polarity reversal. So I just introduced what is Stetter reaction. The Stetter reaction is the generation of the nucleophilic Breslau intermediate. And once the Breslau intermediate is generated, this position, the carbon is nucleophilic, and it can add to a carbon-carbon double bond, which is activated, generating an enolate. Now this enolate can undergo a proton transfer and final release of carbene to form the 1,4-di substituted or 1,4-diketone derivative. Just to answer, Vivek, earlier you asked this question of how this act as a nucleophilic intermediate. So once you have this Brislow intermediate, now this nitrogen lone pair can add from this carbon, which is the acyl carbon, to this 1,4 addition to the beta position of this species, generating a new carbon-carbon bond here, and now a proton transfer and a final elimination of this carbene leads to this 1,4-diketone structure. So this is a typical Stetter type reaction. One can also envision a simple benzoin reaction in the same fashion, where the Brislow intermediate adds to a second molecule of aldehyde. So when we started working in this area of, yeah, please.
We have this aliphatic also, because I just want to know the role of why this cyclic carbene. Like, do we have example of the Brewster intermediate which is having not the N-Heterocyclic carbene but the aliphatic carbene?
No, so that is a very nice question. So the simple acyclic diaminocarbene, although nucleophilic, these are not known to form a Brislow intermediate which can be isolated. Because if you have a secondary amine, say a diaminocarbene, acyclic species, the nitrogen will be also nucleophilic in addition to the carbene carbon. Okay, so you know that if the NH is free in a diamino species, it can directly add to the aldehyde, forming a Schiff base and related intermediate. So that also adds value to the generation of a cyclic aminocarbenes or thiazole derived species or even triazole, which in addition to the rigidity, which does not add from the nitrogen center to the aldehyde. Okay, so when we started working in this area of carbene catalysis using the polarity reversal strategy, the Stetter reaction, as I told, where the polarity reversal, the Brislow intermediate can add to a wide variety of carbon-carbon double bonds. The addition of this Brislow intermediate, this is the polarity reverse species, to simple vinyl sulfones and vinyl phosphonates. These are moderately electron-poor carbon-carbon double bond species, which was not known. So we demonstrated the addition of aldehyde to simple vinyl sulfones. As you can see, for a vinyl sulfone, this carbon-carbon double bond will be electron-poor. So the acyl anion generated from this aldehyde and this thiazole-derived carbene can add to this vinyl sulfone to form a gamma-ketosulfone. This chemistry can be extended to vinyl phosphonates, where gamma-ketophosphonates can be synthesized from a wide variety of aromatic aldehydes. So, yeah.
I have a question. Can you go back?
Sure. Yes.
Okay. So why did you choose this kind of sulfur containing N-heterocyclic carbene?
Yeah. So the thing is that, so if we have a thiazole derived carbene and imidazole derived carbene, it is already known that the imidazole derived carbenes are better nucleophilic than the thiazole derived carbene. So this reaction works with the imidazole derived carbene as well. But when we tried various carbene precursors, we found that the thiazole reacts better than the imidazole under the optimized conditions. So here the thiazole, instead of thiazole, if we use imidazole, that also works, but the yields are in the range of 60s, whereas the thiazole derived carbene gives the product in 80% or more yield. So it is just the optimization. Yeah, Vivek. Second.
Does that mean that the cycles are somehow changing the equilibrium in the carbon?
Yeah, so this is also known. So if you take imidazole, thiazole, and triazole, imidazole derived carbenes are better nucleophilic.
Mm-hmm.
Okay, so better nucleophilicity is sometimes an advantage, but not always, because better nucleophilic carbenes sometimes irreversibly bind to the aldehyde, so that it will add, but it will not come back.
Mm-hmm.
So one cannot get the catalytic applications.
Yeah, that's the rate.
Yeah.
I have a question. Like, if I look into the precursor of the carbenes, those are all aromatic systems, right? So if I take a non-aromatic system, say if I remove the double bond from the CC double bond, then will I will be get to see the same heterocyclic system carbene after addition of the bases?
So what you are thinking is this
Yeah,
carbon double bond.
I will remove the double bond.
Yeah.
Then will
So-
I be able to get the same type of system?
So for thiazole derived species, the saturated thiazolium derived carbenes are very, very unstable. The precursor itself is unstable. We cannot synthesize under room temperature.
Okay.
Okay, so that's why people usually do not use the saturated thiazole derived carbenes. But you are right, with an imidazole, one can synthesize. So if you don't have this carbon-carbon double bond at the backbone, what we have is an imidazolinium species.
Yes.
Okay, so those carbenes are better nucleophilic than a simple imidazolium.
Okay.
Why? Because in the case of an imidazolium, once the carbene is formed, it has to break the aromaticity.
Exactly.
But in the case of imidazolinium, there is no double bond. So one does not have to bother about the aromaticity, and it is better nucleophilic. So these all concepts are known in the literature.
Got it. Thank you.
Okay, yeah. So in addition to Stetter reaction, what I showed you, where the aldehyde adds to unactivated carbon-carbon double bond or electron deficient carbon-carbon double bond. That is called Stetter reaction. So Stetter reaction can also be combined with other known reactions in organic chemistry. For instance, a Stetter reaction can be combined with an aldol reaction to form a cascade process. A cascade reaction is one reaction followed by the other in one flask, which leads to or which can add molecular complexity in a one-pot operation. So for example, Song Ye and co-workers, what they did was they took a phthalaldehyde, a benzene ring having two aldehyde moiety, and an acrylate using carbene and heterocyclic carbene. What happens is that a molecule of carbene will add to one of the aldehyde moiety, okay? And then the polarity reversal happens and generate the Brislow intermediate. And now the Brislow intermediate generated will add to this carbon-carbon double bond, which is electron poor, generating an enolate equivalent, which can subsequently add to the second aldehyde moiety, which is now an acceptor. Okay. And in the process of this cascade reaction, which is called a Stetter and then an aldol process, leads to a diastereoselective synthesis of tetralone derivative. This is known in the literature by Song Ye and co-workers as early as 2013. So we thought, can we use this concept of Stetter reaction followed by an aldol process for a reaction which could lead to the formation of chiral centers, not only point chiral centers, but also an axis. So the idea was to take a dialdehyde, just like Song Ye did, and instead of the acrylate, we use a maleimide derivative with a CN bond containing a 2-tertiary butyl moiety. And when this Stetter-aldol cascade works using carbene catalysis, this could result in the formation of a succinimide derivative with 2-point chiral center and a CN axis. And now this will be a little complicated because the system has two types of chiral centers, point chiral center and an axis. So to make things easier, what we thought was we can destroy these point chiral centers, the two chiral centers, by simple oxidation of this carbinol, which converts this carbinol to the ketone so that this entire part will be now symmetrical. And in the process, the molecule only will have a CN axis. So using a procedure available in the literature, the Stetter-aldol cascade, we envisioned the application of a carbene catalyzed reaction for the synthesis of axially chiral succinamide derivative, CN axially chiral succinamide derivative. And the underlying principle or the thought process behind this process is these axially chiral CN bond containing molecules are having some potential applications. For instance, a marinopyrrole A CN axially chiral molecule is an antibiotic, and there are some sedative, herbicide, and also ligands having CN axially chiral molecule. And we know that the construction of simple biaryls, I'm sure this is a simple MSc chemistry. So if you have a biaryl, two benzene rings connected, then the CC bond can rotate, right? The moment you fix the substituent at the ortho position, the CC bond cannot rotate. So it has some chirality, which we call etrope isomerism, the axial chirality, right? So the axially chiral biaryls are quite well known. And there are several strategies to synthesize axially chiral biaryls. However, the CN axially chiral biaryls, the number of methods are quite less. And when we worked in this area, there are no carbene catalyzed strategies for the CN axially chiral molecule synthesis. And the application is this type of CN axially chiral molecules have important pharmaceutical applications, and some of them are also used as ligands in organic synthesis. So with this underlying thought process, my PhD student Saumen Barik did the optimization of the reaction conditions, and finally he found that the simple reaction of phthalaldehyde with emmalimide using a chiral N-Heterocyclic carbene, so an amino indinol derived triazolium salt derived carbene, and the carbene is generated using Hunix base as the base. And the Stetter-Aldol process, as I told you previously, this afforded the CN axially chiral succinamide derivative in up to 90% E. And this reaction, yeah. Please.
Sorry, Biju.
Yeah. Yes.
I'm a little bit organic
Sure.
chemistry poor.
Yeah.
That carbon that is fused, the single carbon at, yes, that
Yeah.
carbon,
Mhm.
that's chiral, isn't it?
No, it is achiral, right?
It is achiral.
Because all the substituents on this carbon are similar.
Achha, that is similar. Okay, the half.
So what we envisioned was,
Okay. got
say
it.
for example, when we followed the literature procedure of Saulnier,
Okay, now it does not remain. Okay, so you
So-
killed the chirality.
Yeah,
Okay,
so
okay,
what
okay. Right.
the Stetter-Aldol process will initially give
Ah,
rise to a carbinol
Got it.
having this 2-point chiral center and the axially chiral center.
Yeah.
Okay, so our aim was to prepare this type of compounds with a CN axis alone.
Got
And
it.
if you have the point chiral center, typically we have issues of diastereomer.
Yes.
So
Yes.
what we did was we just oxidized this
Oxidized.
chiral
Now
center,
you killed that
then
chirality. and-
both the chiral centers were gone. Okay, so then the molecule contains only the CN axis. And this reaction was found to be quite broad with respect to various malimide derivatives and symmetrically substituted phthalaldehyde derivatives. We tried unsymmetrical phthalaldehyde derivative also, where we got a mixture of regioisomers, and the regio selectivity was very poor, almost 1:1. But with symmetrical 1,2 substituted aldehydes, the yields and inertial selectivities are moderate to good. Yeah, please.
With the substrates that you're using,
Okay, so the optimize the
structure of the catalyst,
Yeah.
the catalyst structure was quite complicated.
yeah.
How do
So
you
this
come to this structure?
So this catalyst is already known in the literature. So we don't do any catalyst engineering. We take most of the time non-catalyst, and the beauty of carbene catalysis compared to all other areas of organocatalysis is carbene catalysis is the rare area where you don't start with a catalyst. You start with a pre-catalyst. Say, for example, in any other area of catalysis, secondary amine catalysis, Bronsted acid catalysis, all these areas, you start with the catalyst. Okay. But in carbene catalysis, you start with the precursor. And you add a base, generate the carbene in solution. So the base matters, the solvent matters, the stoichiometry matters, so many parameters. Okay. And to answer your question, this type of triazole derived carbenes, the architecture little complicated, but 1,2-di or 1,2 amino substituted internols are known, or amino internols are known in the literature. We also synthesize in our lab, and these amino internols are having 2 chiral centers, the cis1R2S or the other enantiomer. We can buy or we can synthesize also. And then in straightforward 3-step sequence, we can easily prepare this triazole derived carbene, which is reported by Jeffrey Bode from ETH. This is already known in the process. What we did was we used this carbene for generating the Breslow intermediate, and the stereo determining step is the first Stetter type reaction. And for this, we did a series of optimization studies. So I'm not showing the details, but to answer your question, this carbene is known. But what we did was we varied different carbene precursors and derived at this carbene. So we screened almost 25 carbene precursors and found that this carbene is the best. To be honest with you, we did not synthesize any new carbene. We only screened the available carbenes known in the literature. And among those carbenes, this carbene turned out to be the best. Okay.
And when you screen all these carbene precursors, along with that, you're also screening your substrate scope, right?
No.
It will work best with these kinds of substrate, not with something.
So what we do is for the optimization of reaction conditions, we screen various carbene precursor, solvent, base, additive, temperature, and concentration. And these all studies will be done with the parent substrate we call. In this particular case, the unsubstituted phthalaldehyde and the malimide derivative. And once we reach the optimized reaction condition, in this case, 70% yield and 90% EE value, then we don't further screen. We take this condition as optimized. So as you can imagine, the carbene catalyzed reaction condition and then PDC and oxidant to make it only as axially chiral species. Okay. And then when we do the substrate scope analysis, we take these reaction conditions and now we vary the malimide in this particular case. And in the next case, we vary the differently substituted malimides and phthalaldehyde derivatives. So we don't do any other change. We take the optimized reaction conditions, try on various substrates, and see how is the change in reactivity and selectivity with respect to various functional groups. Yeah, please.
Molecular sieves.
Yeah, so the molecular sieves, what we have found in these reactions, the molecular sieves enhances the reactivity a little bit, because normally we use dry toluene, but it always contains some traces of moisture. So this can be absorbed by molecular sieves as a species which takes the moisture from the reaction solvent. So we usually get around 5 to 6% an enhancement in the reaction yield of the product using molecular sieves as an additive. Okay. So yeah. Sorry. Yeah, NHCs.
Axial chirality.
Uh-huh.
So how do you calculate? It's not EE also, it's ER.
Yeah, this is ER. So this is what we get in HPLC using a chiral column.
Yeah, but what could be the other isomer?
Say for example, this is 94:6 ER. That means 88% EE, enantiomer ratio. Enantiomeric excess, 88%.
That I understood.
So 94% one enantiomer, 6% the opposite enantiomer.
What is other enantiomer? Because I see only the axial thing.
Yeah.
So what is the other enantiomer?
Other opposite enantiomer, I will come to that.
Oh, yeah.
Just I will show you the possible enantiomers. So the thing is that in these processes, what will happen is that when we do this reaction without oxidation, we have the concerns on these 2 point chiral center and the CN axis. So since we have 2 point centers and 1 chiral centers, we can expect 8 stereoisomers because it is equivalent to 3 chiral centers, right? So what we did was we did an oxidation to kill these 2 centers so that it is only having a CN axis. And the process is enantioselective. And to completely answer your question, I will come to the next slide.
There's one more question.
Yes.
My question is, you're using molecular sieves
Mhm.
just to prevent any moisture in the medium.
Yes.
So it may be possible that if you are getting enhancement in the product, then water may be as a byproduct in your.
No, water is not the byproduct. So the what we were afraid is our dry toluene may contain traces of moisture that can kill the catalytic activity of the generated carbene. We cannot rule out that possibility, right?
How it will do that?
I mean, so
The carbene reacts with water.
carbene can be quenched by moisture present. So but your question is how water can enter into toluene, right?
No. I think how the reactivity of the carbene.
Yeah, so the generated carbene can be protonated by water molecule, right? Okay. Yeah. Sorry, there is something happened.
Sorry, just clicking. Yes. Okay.
Sorry, JD.
Now do it.
Okay.
It should be controlled, right?
Let's just keep it.
No?
Now it seems okay. Yes. Yeah, so this reaction proceeds via the generation of this free triazole derived carbene from the triazolium salt. And once this carbene is generated, it adds to one of the aldehydes of this aldehyde moiety of the phthalaldehyde, generating the tetrahedral intermediate. The same thing I told you in the beginning, a flat aldehyde is converted into tetrahedral intermediate. And now a proton transfer will lead to the generation of this enaminol or the nucleophilic Brislow intermediate. And now the Brislow intermediate thus generated is nucleophilic at this particular carbon, right? And that nucleophilic species can add to the electron poor carbon-carbon double bond of this malimide, generating this amide enolate with the formation of a new carbon-carbon bond. And this amide enolate can probably undergo a proton transfer to generate a more substituted amide enolate. And this can undergo an intramolecular aldol process to form this carbinol, the same Stetter aldol pathway as I told you in the beginning. And once this carbinol is generated, it can be oxidized to the desired product. We also considered the possibility of an aldol process in the absence of NHC. So at this stage, when the carbene eliminates before the aldol process, so the elimination of carbene could result in the formation of this intermediate aldehyde, and this can again cyclize to form this carbinol. So there are two pathways where the aldol happens in the presence of a carbene or the absence of a carbene. So to get more insight into this process, we seek the help of my colleague Garima Jindal, who is an expert in DFT calculations. And what she found was the pathway 2, where the aldol reaction takes place in the absence of carbene, is better stabilized by 5.4 kcal per mole. which gives some information to us that the aldol reaction proceeds in the absence of NHC and leading to this carbinol, which is subsequently oxidized to the desired CN acylic iron form. Room temperature, 25 degrees. Yeah, feel free.
Paraaldehyde. Why you will NHC be reacting with one aldehyde? Both of them are equivalent.
Yeah,
So in the,
so
in the
this
very
is
first step, it could be some sort of a dimer, right? Both the aldehyde can react.
yeah. So this, if you take a simple phthalaldehyde, it is symmetric, right? Both the aldehydes are equivalent. So that is what I said. So when we did the reaction with so when we did the reaction with a symmetrically substituted phthalaldehyde, so you can see that 3,4-dimethoxy or this heterocyclic or naphthyl or anthracene moiety, we get a single isomer. But the moment we have an unsymmetrical this phthalaldehyde, we have the issue of regioselectivity. The same thing what you are telling, the two aldehyde moieties are non-equivalent. So we get two regioisomers, and typically the regioisomer ratios are 1:1. So poor regioisomer. Okay. Yeah. So if you look at this 2-tertiary-butyl aryl maleimide derivative, if you look at the structure of this molecule, and if you view through this tertiary-butyl group, this molecule has two atropotopic phases. What are atropotopic phases? The two phases through which a nucleophile can add. Say, for instance, a nucleophile can add from the Ca carbon or the Cb carbon, which will lead to the formation of two enantiomers. This is what Vivek was asking. Why you get a single enantiomer? What is the other or opposite enantiomer? So, in general, a maleimide derivative, this molecule is symmetric, right? And we can break the symmetry by introducing a substituent at Ca or Cb. And if the nucleophile add to Cb, you get this product. If it adds to Ca, you get this product. And these two products are mirror images, two enantiomers. Okay. So in our case, what happens is the nucleophilic Breslow intermediate, which adds to the rephase of the molecule, atropotopic rephase of the molecule, which leads to the formation of this particular enantiomer after oxidation, the M helix. But the atropotopic psi phase addition to the Ca carbon will be inhibited by the amino-indinol core of the catalyst. And that is the reason the enantiomer, the opposite enantiomer, will not be formed under our reaction condition, which leads to the enantio enrichment or the enantiomerically pure single product formed in this process. Yeah, please.
Is this the tertiary carbon center that governs the stereoselectivity, right?
Sorry?
That governs the stereoselectivity.
So the role of tertiary butyl group, I'm coming to that. So we need the tertiary butyl group. I'm coming to that in the next slide. So yeah, so this accounts for the single enantiomer formation and the non-formation of the opposite enantiomer by the tuning of the catalyst structure by means of the sterics. One of the atropotopic phases of the maleimide is blocked and only the single phase addition happens. So we also try to get some information on the stability of this molecule. So we all know that the carbon-carbon and carbon heteroatom bonds can rotate at different temperature and depending upon the rotational barrier. And in our case, we synthesize this succinimide derivative with a CN axis. And this CN axis, the key to success for the CN axis stability is the presence of the 2 tertiary butyl group, because that 2 tertiary butyl group will inhibit the CN rotation. So which means once it is in a locked conformation where this 2 tertiary butyl group is like this, it cannot rotate. Okay, and we also found that this rotation, CN rotational barrier, depends upon the temperature. How? At room temperature or even at 40 degrees Celsius, when you take this reaction product and heat it at 40 degrees Celsius, we did not see any erosion of EE. That means the CN bond is stable at 40 degrees. And we did this experiment up to 90 degrees and found that the EE values are consistent. That means up to 90 degrees, the CN bond does not rotate, or the CN bond is stable to rotate. It does not rotate. But beyond 90 degrees, we found that the CN bond, the EE values are dropping, and at around 150 degrees, there is almost no enantiomeric excess or no EE. That means at around 150 degrees, the CN bond can freely rotate, and the rotation will destroy the selectivity. So at 150 degrees, this compound is almost racemic. We also found that, Kalay.
When you are done by taking the product.
Product.
But you didn't perform the reaction at high temperature.
Sorry?
You didn't do the reaction at high temperature, right?
No. We did not do the reaction at high temperature.
So
this is just, we want to know at what temperature or up to what temperature the CN bond is stable and the E will be persisting.
okay, if you go back to your mechanism where you form your first step. Okay, here. So here also you will have your first enantiomeric formed, right?
Okay.
That also can undergo rotation even before going to your final product. So where you start your first the asymmetric synthesis step.
So the first enantio determining step will be the addition of this Brislow intermediate to this carbon-carbon double bond.
Okay, that in this one, before it going for the second attack even. So this can rotate, right?
That we don't know, because what we did was we say, suppose this is the outcome of the carbene catalyzed process. We have 2 chiral centers, point chiral centers, and a CN axis. What we did was at the end of the reaction, we oxidized so that these 2 point chiral centers are gone. So we have only axis. Okay, so the reactions are performed at room temperature. What I want to say in this reaction, this experiment, is we try to see how stable is the CN bond, or what is the temperature sensitivity of the product. And we found that up to 90 degrees, this product is stable in terms of rotation, CN rotation. So after 90 degrees, the E value is dropping. That means further heating makes the CN bond rotating so that the E is dropping, and at around 150 degrees, it is almost racemic. That means at 150 degrees, free rotation is happening. Okay?
Can you go back? Yes, just Biju, just can you tell me how the C and the RE phase are slightly different in interactions with the sub?
So this here, what happens is that, so we believe this is exactly from our observed enantiomer, the crystal structure of this enantiomer. We feel that the atropotopic rephase addition will lead to the product after oxidation, this type of product, which is in agreement with the X-ray structure we got.
Okay.
With the X-ray
structure, you compared what the final thing was.
Because
but can you rationalize it? Can you rationalize this?
Only through X-ray analysis, we confirm the enantiomer, a particular enantiomer is formed and opposite enantiomer is not formed. Okay. So in this particular case, say, for example, when you consider the amino-indinol core, here it is projecting above the plane, and the nucleophilic addition from the bottom phase here is feasible, compared to from this opposite direction where the amino internal core is now projecting below the plane. And above attack is not feasible because of the tertiary butyl group. So a logical explanation based on the single crystal X-ray analysis, where we get information of the particular enantiomer formed in our reaction, where using this structure, we can explain only the atropotopic rephase addition leads to the product, and the psi phase addition is not giving the opposite enantiomer.
Do you have some computations to show either of these two transition states have slightly different energies?
Yes. So Garima did the DFT calculations. So she generated the transition state leading to the rephase and the psi phase addition. And according to the DFT studies, the rephase addition will be the low energy transition state. Yeah, we have all DFT evidence that this reaction proceeds in this fashion. Okay. Yeah. So another thing what we did was we also tried to calculate the rotation. Yeah, please.
It is stable after 160 degrees Celsius.
Sorry?
Is your catalyst stable at 150, 160 degrees Celsius?
We did not try. We did not try.
Then how you draw that? Yeah.
So this is just, we take the product. So what we want to know is, so under our reaction condition, this product was formed in 90% E or 95.5 enantiomer ratio. So we want to know how stable is this CN bond. And we know that this tertiary butyl group at the 2 position is required because that will prevent the free rotation. And another way the rotation can be enhanced is you provide more energy. So what we did was we took this product in toluene and heated. Say at 40 degrees, we heated this reaction, this product, and we did not see any change in E. Up to 90 degrees, it was the same. But beyond 90, what we found was the E is dropping. What does it mean?
There was no degradation of the molecule.
No, there is no degradation. The product is stable. But remember, this is not using carbene catalysis. You take the product of the reaction. Okay, so from 90 degrees, when you increase the reaction temperature, the E is drastically dropping. That means when you heat beyond 90 degrees, CN bond can rotate.
And one more question. In your mechanism slide, I did not get where the water is creating, where water can create a problem. Because your
water can not create problem in the catalytic cycle. The carbene generated, so carbene is nucleophilic, right? So the carbene can be the OH minus, or the carbene is nucleophilic, right? Yeah. The nucleophilic carbene can pick the proton from water.
Okay.
And thus it will be degraded. So the catalytic activity of the carbene will be gone. Okay. Yeah. Okay, so we also, I hope I can take a little more time.
Yes.
It's exciting. So please feel free to disturb me.
Okay.
Yeah.
Can we do it in 5 minutes?
Okay, you can stop me at any time. So yeah, we can. Okay, perfect. Anytime you just tell me to stop. Okay. So what we also did was we tried to determine the rotational barrier for the CN bond. And following a procedure of Dennis-Pick-Curran, what we did was, with respect to temperature, we found that beyond 90 degrees, the EE values are slowly dropping, right? So we fixed a particular temperature, in this particular case, 100 degrees Celsius, and we heated the product at 100 degrees Celsius and noted the change in EE value with respect to time. And following this procedure of Dennis-Pick-Curran, there is an equation which I forgot, which one can easily determine the rotational barrier And we calculated using experiment as 32.4 kcal per mole. So the rotational barrier for the CN bond is almost 32.4 kcal per mole, which was almost confirmed by my colleague Garima Jindal using DFT calculations. The calculated value is almost 34 kcal per mole, which is more or less in agreement with the experimental value. We also tried to get information on the role of tertiary butyl group, because I should confess that this reaction works only when the tertiary butyl groups are attached or a bulky group is attached. To make sure that that is required, we did the reaction with isopropyl and methyl substituent at the 2 position. The reaction worked in moderate yield, and you can see it is just racemic. That means instead of tertiary butyl group, if we have either the methyl or isopropyl groups at the 2 position, the CN bond can easily rotate. That indicates that the compound formed is racemic. Yeah, Ankada. Yeah, we try to lower the temperature. The problem is that we lower the reaction temperature, perform the reaction up to minus 20 degrees Celsius, but when we take the product for HPLC analysis, that will be at root. And we don't know at what stage it is happening, but we don't have any technique to check the HPLC at a lower temperature. Okay, so we performed it to make sure that this reaction is not sensitive with respect to temperature. Absolutely. No, they have only axis, right? A single axis. So for example, before oxidation, we have different NMR because we have diastereomers. Okay. So that is why this rotational barrier, we can also calculate using NMR technique, but we use HPLC technique because NMR will give the same spectra for both enantiomers. Okay. Mamshi, yeah. Yeah.
Yes, there was an inversion at nitrogen.
Inversion?
Yeah, at nitrogen.
Yeah.
If there is an umbrella type inversion there, is it possible there or it's not?
No.
It is sp2.
It is, yeah, it's sp2. So, but there is no inversion possible here. The only thing is that the tertiary butyl group can be either projecting above or below. These are the 2 possible enantiomers.
Okay.
Yeah. Good. Yeah.
If you have your R is methyl, then there is a possibility for suprafacial and antrafacial top and bottom addition also, right? Then you get 4 isomers.
When it is R is equal to methyl.
R is methyl. Now, in the alkene, the new substitution can happen from the top and bottom, right?
Yeah. So what you are telling is correct. So what we always consider the atropotopic phases means the 2 tertiary butyl group will inhibit the top phase addition. But you are right. When it is methyl, the extent of steric hindrance is less. It could also be possible, but nevertheless, we got 50-50, so we didn't bother about it. But we believe that in the final product, the CN bond can rotate. And to get information, further information, why there is no selectivity with methyl and isopropyl group, again, I seek the help from Garima Jindal to calculate the rotational barrier for methyl and isopropyl substituent. And it turned out that with methyl, it is 22.4 kcal, and with isopropyl, it's almost 24. The low rotational barrier for methyl and isopropyl compared to the 32 for a tertiary butyl accounts for the rotation for methyl and isopropyl substitution. In summary, what we have demonstrated is the atroposelective synthesis of succinimide via a carbene catalyzed desymmetrization strategy. So now I showed you a I'm looking at JD's face. 5 minutes?
Yeah, okay. Fine.
I have several slides. I never thought that it will be this much discussion. So I enjoyed. So
Got the mechanism also.
Okay, perfect. Yeah.
So maybe you can demonstrate a little bit.
Yeah. So this the next one you will like. So what we demonstrated was Now we took a malimide derivative having a 2 tertiary butyl group. And what we did was we broke the symmetry of this molecule. Okay. So this molecule is symmetric. So if we run an HPLC of this molecule, we get a single peak because it is symmetric, achiral and prochiral. So you need one transformation to make it chiral. So assume that you break the symmetry by introducing a substituent at this one of this double bond, for instance, a methyl group. Okay, so now the molecule is not symmetric, it is chiral, and if there is no element of chirality in the synthesis, this compound will be always racemic. How we can prove it? If you take a HPLC, it will separate the two enantiomers. So in the top case, it is symmetric. Now it is unsymmetric. So we thought, can we use this unsymmetrical system where we can introduce a substituent at the olefin terminus of a malimide, specifically an amino moiety. And this amino moiety is now conjugated with a carbon-carbon double bond. So it is a enamine moiety, a 3-carbon moiety, which can be utilized for a different carbene catalyzed intermediate, an alpha-beta unsaturated acylosodium, in a 3+3 process. How? If you take an aldehyde, an alpha-beta unsaturated aldehyde, and you add a carbene, you get a conjugated Breslau intermediate. Just like an aromatic aldehyde, you extend it to an alpha-beta unsaturated aldehyde. And once this Breslau intermediate is generated, you oxidize using a stoichiometric oxidant to form this alpha-beta unsaturated acylosodium. And now this enamine moiety can add to the beta position, and this carbonyl position can add to this amino moiety in a 3+3 fashion. So in this process, what we can observe is an efficient kinetic resolution of this malimide, because this malimide is now racemic 50-50. Only one of the enantiomer will react with this azolium species, leaving the other enantiomer intact. So why we did this reaction? Because we have some experience with this alpha-beta unsaturated acylosodium chemistry over the years. We use this single intermediate for the construction of various heterocycles and carbocycles. So what we did was we generated this alpha-beta unsaturated acylosodium using an oxidized enal and using an amino substituted malimide. Only one of the enantiomer react with this aldehyde to form a dihydropyridinone, which is formed in reasonable enantioselectivity and diastereoselectivity, leaving the opposite enantiomer untouched, thus leading to a kinetic resolution. So kinetic resolution means you take a racemic mixture, you react specifically one of the enantiomer, leaving the other enantiomer unreacted. And this reaction was also quite general. We got really good substrate scope and functional group compatibility. And this reaction proceeds via the generation of free carbene and this key alpha-beta unsaturated acylosodium intermediate. And to this, the amino indanol can add in a Michael fashion to form this key intermediate, and then a cyclization lead to this desired product, where the opposite enantiomer of this malimide will be not reacted or will not react, and only one enantiomer will react. What we feel is that this is the enantiomer, the catalytically active alpha-beta unsaturated acylosodium. So the malimide adds from the bottom phase of the molecule because the top phase addition is hindered by this amino indanol core. So only one of the enantiomer will react, but the opposite enantiomer, the top phase and bottom phase addition will not happen. So that leads to the kinetic resolution strategy. So probably I will stop. I don't.
There should be some
some chance for discussion and some snacks as well.
Oh, okay, good. So I have more slides, but
No, it's fine. We will keep you for another
sure,
another talk. But
at least I have to show
Sure,
some
sure,
faces.
sure.
Because,
Sorry.
otherwise I'm not doing justice to
sorry.
my students.
Yeah.
Yeah, although I showed the key players in most of the slides, but I should appreciate the continued or the hard work of all these students. So this is our present group. So I mainly highlighted the work of Sauman Barik, a fantastic in PhD student in my group. He's the key for all the CN axial chirality. And Balanna, he's now a postdoc with Armido student at Münster. He demonstrated the NN axial chirality. Then Shilpa Barik, Sayan Shi, and Abhishek Guin, they are also working in carbene catalyzed reactions. And the rest of the students are working on benzene chemistry. And I should also thank various funding agencies for their continued support. And finally, JD for the invitation. And it was really nice coming to TIFR for the first time. Wonderful place. And thanks a lot for your kind attention. And apologies, I was not able to complete everything. I will be very happy to take more questions if you have.
There's a warm round of applause, please, for Biju. Before we quickly go to the questions, can I get the question on the chat, please? Once there's a question in the chat. Okay, so in the mechanism, why the carbene always attack the carbonyl first instead of the conjugated alkene?
Why in the mechanism, why this carbene always attack carbonyl group first instead of conjugated alkene?
Okay, I think you were talking about the aldehyde. So the person is.
So if we have a simple aldehyde and alpha beta unsaturated aldehyde, the electrophilic center of an aldehyde is the carbonyl position,
Right.
And compared to the beta position
Of the
so obviously the carbene prefers addition to the carbonyl position.
Yeah.
But having said that,
you can also
if we have an alpha beta unsaturated ketone,
yes,
this can be reversed. This is known in carbene catalysis. So, but the question is alpha beta unsaturated aldehyde. So the aldehydes are little more electrophilic than ketones. So the beta position attack is less preferred compared to the carbonyl attack.
Got it. Thank you, Anonymous, for the question. Okay, so now questions from the lecture room, lecture theater. There are no more questions? Okay, then I have a last question before we move to the snacks. Can you explain again the last reaction? It was tough for me, like the resolution.
Kinetic resolution.
Yes.
Yeah, sure.
Why was it pre-selecting one of the racemic, one of the enantiomers?
Yeah. I cannot, I'm sorry, I have to use pointer for.
Yeah. It's okay. It was a very nice concept, but I didn't understand.
Yeah, I hope I can.
Why did one of the enantiomers only?
So the key thing is, so if you understand these two models, you will understand.
Right.
So the key alpha beta unsaturated acylazolium, I kept it at the top, and the amino indinol in a different color at the bottom. Okay. So if you look at this alpha beta unsaturated acylazolium intermediate, because of the amino indane core, the amino indane is always projecting above the plane. Okay. So the top face of the molecule will be shielded by the indane moiety.
Okay.
So the nucleophilic attack of this enamine can take place from the bottom face, but the top face addition cannot take place. So that's why we observe. So the bottom face addition happens, the phenyl group will go above.
Okay.
That is why we get this dihydropyridinone intermediate.
Okay.
On the other hand, if you take the opposite enantiomer
of the unsymmetric.
This is particular enantiomer of the maleimide where the tertiary butyl group is projecting above.
Backside.
So for the enantiomer, the tertiary butyl group is projecting below.
Right.
So in this particular case, again, the amino indane core will inhibit the top phase addition.
Mm.
And now the tertiary butyl group is projecting below the plane.
Mm.
So the enamine addition from the bottom phase also will be inhibited.
Okay, this is hard for me, but it's okay. Yeah.
But
okay.
here the tertiary butyl group is projecting
Hmm.
above, so the bottom phase addition is
Okay.
feasible.
Okay.
So that is why this particular enantiomer reacts from the bottom phase, but this enantiomer cannot react
Cannot
at
because
all.
there is already some.
So this enantiomer of
Yes.
this maleimide will come out of the catalytic cycle untouched. And that is how the enantio enriched
Mm.
maleimide with the tertiary butyl group projecting below the plane
Mm.
will be unreacted, or it will be enantiomerically pure. But the tertiary butyl group projecting above the plane will react to form a product.
Right. Okay.
Hope it is clear.
Yes, I got the idea.
Yeah.
Typically, we use for kinetic resolution in NMR also, we make diastereomers by adding two chiral. So the one molecule is chiral, the brown colored, this.
No, this black colored is chiral now. because-
Chiral now. Okay.
Yeah.
Right.
So this one
Right.
is racemic.
Racemic,
So
but that is fine. Now it is fine.
Jedi.
Sure.
So this is one of the enantiomer
Sure.
where the tertiary butyl group is projecting above.
Correct.
This is the opposite enantiomer where tertiary butyl group is projecting below.
Sure.
So this enantiomer does not react. And that's how
Got it.
this enantiomer is recovered.
Recovered. from
And
the
this
reaction.
enantiomer reacts in a 3+3 annulation, forming a 6-membered ring.
Ring.
So it
And
forms.
you isolate that, and this is becoming pure, chirally pure.
Absolutely.
Yeah. Okay.
So
fine.
a resolution has happened.
Yes. Thank you. Any other question?
Yes.
Yes.
In these two additions that you have shown over here,
Mhm.
the below one,
Mhm. Here.
where the tertiary butyl group is facing backwards, right?
Yeah.
It is towards the ring.
Yeah. So the
That
tertiary
means-
butyl group is projecting below the plane.
Below the plane, right?
Yeah.
So won't that be a bit of steric hindrance between?
No,
the-
below the plane, since the tertiary butyl is projecting below the plane, so that the alpha beta unsaturated acyl acyloleum, the top structure, bottom phase addition is feasible. Only the top phase is shielded by the indane. Okay. But here, the amino indane, the maleimide, since the tertiary butyl group is projecting below the plane, the approach of this enamine to the beta position will be less feasible. This is just a model we suggested to explain the kinetic resolution phenomenon. Because this enantiomer does not react, and we got it enantiomerically enriched. Okay.
Okay. Let's thank Biju once again, and we all can proceed for a little bit of snacks. Biju, it was fantastic talk, and thank you for doing this for us. Oh.
Thank you. Thank you all for joining.
Yeah. There's one idea I did not